Here we are again. It is the Natural Science 116 video lecture. Natural Science 116 video lecture 8. And we're going to talk about the laws of electricity and magnetism. So let's get started. We ended up with last time talking of looking at electricity and magnets in particular. So we'll review a bit of that. But I want to get the whole set of laws of electricity and magnetism just in really compact form. Let's start with electricity. So what do we know about electricity? There is a positive and a negative charge. There's a force between those charges. So we'll write positive and negative charge. Force law. What else do we get out of that? Well, the charge Q is a coulomb. So that's a new quantity in physics for us. And we had some actual practical applications. So I'm going to say force law and therefore energy or work. So yeah, what did we have? We had work is Q delta V when you had charge separation. From that, and coulombs and volts, okay, joules. From that we had power equals Q over T delta V, because power is work over time. Okay, but this was current times voltage, and so we learned that watts is amps times volts. So this, and then also Ohm's law for simple circuits, and that was delta V is resistance times current. And the picture that went with this was we could have a battery here, plus and minus terminals, a light bulb giving off light, and we could hook it up like that. And the schematic for this was our battery, our resistance. So there's our delta V, current, resistance. Okay. So this covered a lot of practical household applications. These two things right here. And I'm actually going to demonstrate an example. You see I have a little bit of stuff here on the table. Good, so that's what we know about electricity, and let me reiterate, this is something we've practiced and we should know how to do for the exam. Okay. So these formulas, roughly what they mean and how they're dealt with. We've done a few problems like that. So there's our knowledge of electricity so far. However, I also had the electric field. And we're going to call it vector E. So the electric field is a vector, and it's what's there when you have, say, a positive charge. If you locate a positive charge here, you have a bunch of field arrows pointing out. Put another positive charge there, is going to be repulsion. So that's what's going on in these scenarios right here. There's actually an electric field, and force is equal to, just to tie this in completely, where force is equal to Q times E. We're not going to calculate with that, but for completeness, we've got this electric field and its applications. Okay, so that's the electric field. Now we're going to talk about magnetism. So second on our list is magnetism and what we've learned about it. I brought out some magnets last time. I actually have a couple little magnets there on the table as well that I'll demonstrate in a bit. But for now, so point 2 in our list, magnetism. And for that we can imagine we have a bar magnet with a north and south pole. And we have the attraction and the repulsion. We learned we can never actually separate a north and a south pole, so that we have the north in one hand and the south in the other. Unlike with the electric charge, where we can't have the plus and the minus separated. Then we discussed the iron filings and the picture that we get. I showed it to you with the compass needles, that the magnetic field, so magnetism and the B field. So the magnetic field is going to be called the B field. We'll use E for electricity, B for magnetism. Okay, so we had some understanding of magnetism, but what we want to do is talk about their combination, because when they come together, they develop interesting phenomena. So my third point here is a fact about electricity and magnetism, and that is the magnetic field. So it's a vector field, means it has direction, right, arrows. The B field acts on moving electric charges. In particular, what that means is that if you have a current carrying wires, so a wire with moving electric charges in it, and a magnetic field will act on it, and there will be a force. Okay, it will move that wire. An individual charge will be moved by a B field as well, but the charge has to be moving electric charge. Okay, so that's a force on the charge Q. Okay, so that's a law for which we have a lot of demonstrations. And you know what I would say for homework? See if you can find some information with a nice image to print out on this. I'll just write homework image for this law. You type this law in, and then you should be able to find something interesting. Okay, so that's point 3. Point 4 is that it's kind of the converse of this, and that is that an electric current produces its own magnetic field. Okay, so an electric current produces, all right, its own, here parenthetically, magnetic field. And there again, you can have all kinds of really interesting demos that we have backstage here. See if you can get some image examples of this. Okay, because that's a really interesting case. In particular, a straight wire current produces circular magnetic fields, concentric circular magnetic fields, and what's called a solenoidal current. So if you have a current in a wire that's wrapped around something, I'm going to grab another color for this one, it will produce a magnetic field that looks just like this one up here, which is kind of amazing. So you'll actually get this magnetic field of this type, and you can even get the same pattern with iron filings that you got with your bar magnet off of this current magnetic field. So electric current produces its own magnetic field. Here I'll write B in blue, and here as well, magnetic field. So yeah, it shows that these electricity and electrical and magnetic phenomena are very close, intimately intertwined. Okay, so that was my 4th point, and my 5th point will kind of complete the entire set, and that is changing B produces changing E. In the sense of oscillations, if you have an oscillating B field, you're going to get an oscillating electric field. So oscillating magnetism, oscillating electricity. And there's more to it than that, but I'm just going to write here, we're talking about oscillations and Faraday's law. So look up Faraday's law as well. If you look up these points here, you're going to get a really interesting set of images, and they're rich phenomena. Here right now I can only show you a couple. Okay. So those are the laws of electricity and magnetism. The ones I erased there having to do with electric currents, those of course we want to actually have some skill with, because we'll talk about them on the exam. These we have to know to move on. So we've got the magnetic phenomena, and then we have the fact that the magnetic field acts on the moving electric charges. The moving electric charges, as I say, electric current, produce a magnetic field. And then if you've got changing B fields, say oscillating B fields, you get oscillating electric fields and vice versa. So really tied together. Now what we need this for is to be able to understand the electric motor and the electric generator, which is a major part of our whole energy discussion. Okay, so we needed this. Like I said before, part one here with the electricity is just good household knowledge, but the combination of electricity and magnetism allows us to understand the motor. And I have the motor on the table here. It's not even assembled yet, and that's what I'm going to put together next. Put together a little motor for you guys. Let's see how we're doing time-wise. We should be able to pull this off very nicely. Good. So, I want to show a motor, and I'll carry it closer to the camera once I have it built. But as far as we can see here, I just have a battery. I have these flat magnets, and I have 3 of them. And you can see that they're magnets. They grab, but if I turn it around, oops, wrong way. I can push them around as well. Here, let's go this way. Okay, so it's a magnet with repulsion and attraction. Good. So we're going to have electricity and magnetism. We have a battery for the electricity. These are conductors, copper wire, and this was the project that we were going to all have for our kit, because you see it packs flat, and we were going to have this in our kit. You may have to come back some other year and I'll make you one. But this is going to be a very simple and transparent electric motor in its functioning. Okay, so I just put these copper wires in this board here to support them, and I'm going to put the battery in here and briefly discuss what I now have. Okay, so I've got a battery plus on one side, minus on the other. And so I should be able to light a little light bulb between these 2 points here. Let's go back to my picture of the light bulb circuit. And of course I just have a really tiny light bulb. We'll see what I can do to show this to you guys. Okay, but the circuit that we were looking at that I'm going to draw again, in this case I have a battery, I have a C cell, so there's the battery, and I'm taking a wire and a wire, and there's the shell of the light bulb, filament inside, there's the bulb. So you take one wire to the tip here on the bottom, and the other wire comes in and hits the shell on the side, okay? This is the plus side, the minus side of the battery. So that's how you get a circuit like this. And since it's going from one side to the other, if I were to get a light bulb between here, we'd be good. Now there's another chance to do this. This is sort of a test. If I put the tip of the light bulb on one end here, okay, and I only have one wire here, so I'm a little bit handicapped, but if I bring this into the shell, I'll get a little bit of light glowing. We'll see if that shows up in the video, okay? Good, so I can do that on this little frame as well. Once I demonstrate this, I'm gonna explain this. So this electric motor, it has a voltage source, and I'm going to connect a wire across this thing and spin it. Well, it'll spin here, but it'll stop spinning. It's lacking the magnet. So now I take a magnet and away we go. So now we have a spinning, functioning motor. It's gonna need a little explanation. I'll bring it up here. Hope this is visible. Okay. So this thing is spinning, and it required the battery, and I can either speed it up, or if I turn this battery over, this magnet over, I can actually slow this thing down to a stop in reverse direction and stop. Okay. Now that happens because if I take, well, I gotta explain that on the board. So this is just a demonstration. We've got the battery. Okay, we've got the magnet, and we've got the spinning loop of wire. This is your major civilizational technology right here, okay. Okay, we'll see how much that comes out. So yeah, there's our motor motoring away. So a little description and explanation. Take this off, because that clearly is a bit small to see. So this is our circuit that we've done before. And now the simple motor. So the simple motor has a battery down here. And we bring up, and I'm just gonna say we've got a little conducting frame. So this is conductor on both sides attached to the battery. So if we put a light bulb here, we could make it glow between these things. Now what we've done here with this loop of wire is actually take insulated wire, wrap it around the C-cell battery. It's insulated wire, and it's scraped off, and maybe I can show this, maybe not. It's scraped off on one side, so if I hold this up close, you could conceivably see some shiny copper. And if I turn it around, you won't see the shiny copper, you'll see the red. Okay. So how does this motor work? And then right here I have to put a magnet, and I'll just say north-south. So that's a magnet, and it has B field going like this. Okay, here's my conducting loop of wire. So we have a current flowing through this loop. And then we had that law that I just erased. The B field acts on that current and makes that loop twist, have some torque. Does a half twist, and then the conduction is gone. It twists through, and then it has conduction again and a current. So the current is interrupted, and that keeps this thing twisting in the same direction. So yeah, we've got the magnet, which has a B field. We've got current in this loop of wire, and because the B field acts on the current in the wire, it produces a torque. So let's go ahead and put this in words. B field acting on current I in the loop produces a torque. And you guys know torque is force times lever arm, so you get a torque, which is a twisting force, and away we go. So that's our motor. That is our simple motor. And like I said, I'll get one for you guys someday if we meet up again. Good. Now another point to be made, and I'll just stand here and make it now, is the following. So this was and is a motor. Put this back in here, and there you go, it's spinning. If I take the battery out, I no longer have a motor, of course. But in principle, if I take the battery out and hook wires up to this, I would be able to twist this loop here, and I would be the motive force, and this would be a generator. So a motor can be a generator, okay? A motor can be a generator, and that's an important property too, and I'm going to illustrate that with some of these devices that I brought. Okay, so now we've got our very simple motor running here. And now I have some packaged motors that we can no longer see what's inside. This one here with the propeller, I'm going to make the propeller spin using a generator here. That's simple, right? Turn the generator, generate electricity, get the electric motor to turn. Reverse, reverse. Let's see. Slow. There we go. Good. Wow. Propeller fell off. Fine. Now, so this was clearly a generator. This device I have in my hand, turn it. It's a generator. This is an equivalent one. Let's see if it works. So I have two generators. Turn the handle, propeller. Okay, so this is also a generator. Now what's really interesting is that these two pretty identical generators, I can hook one up to the other. Okay. Now I'm going to turn this one. Okay, so now this is the generator and this is the motor. Okay, I can hold them both in one hand. Okay. So generator, motor, of course I can reverse it, turn this one, and now this is the generator and this one's the motor. So we talked about generators and motors back when we were talking about pumped storage, hydroelectric power, and there's your concept right there. Okay, so we got the generators and the motors. This one is really the most transparent of them all. You build one of these, you can actually feel the little forces with your hand. If this thing is running, I can actually hold these magnets here and feel the little power pulses. So this is the most transparent in terms of its functioning, this electric motor here. Good, someday we'll make one of these together. Good, so that's generators and motors. Put this back up here. So now I can wrap this discussion up now that we've seen everything. Okay. Right here. Put that right there. Let's check the time. Okay, good. We've got the circuit, we've got the simple motor. Just want to wrap this up now and also say where we're going from here. So yeah, this is a huge subject, and I've given you a very short presentation of it. But we had to have this because of our whole hydroelectric discussion and what's going to follow. So let's kind of summarize this. We have motors and generators, electric motors and generators. Okay. And the point of the motor has been made. With the generator, I have to make another point. First of all, it was the motor in reverse. So for the generator, I apply a force and a twisting force and a torque, and it generates electric power. But what it gives us is electric alternating voltage. Okay. The difference between a battery and our wall outlet is the difference between direct current DC and alternating current AC. So alternating voltage or current. So you've got, it's called AC versus DC. This is from your electrical generator where something's been twisted, something's been rotated, turned. DC would be from a battery. Okay. Now this is really important when we think about generation of large scale power. We were talking about hydropower, and I'll remind us of our hydropower discussion. Remember, we had the lake, the dam, the penstock carrying water down to the powerhouse. Yeah, well, what was in the lower lake here? What was going on in the powerhouse was that a generator was being rotated. And so with these generators, what we have now learned, generator with an N. Actually, let's try writing that again. Generator. What we have there is rotating magnets and coils of wire. So as humble as this thing is, it has the actual property. You've got rotating, you've got magnets and coils rotating. You can do it both ways. You can rotate the coil and hold the magnet fixed, or you can hold the coil fixed and rotate a magnet in the coil. But that's what's there. And there's a, so it's producing power. Okay, let's write the power aspect down here. If you're generating power, that's work per time. Okay. So you're generating power, work per time. And what is supplying the work? What's supplying the work is this water, the immense masses of water that are flowing through here. Okay. Immense masses of water, and the tunnels could be as big around as this room. And so that's why when we measured those wattages, you may remember we were talking megawatts and even thousands of megawatts. That's from that immense volume of water going through the generators, or turning the generators. And that much power is needed if that much power is being drawn downstream in the civilization. So there's a resistance that kicks in. This is a really important demo, but you guys aren't here to experience it. I'm just going to describe it. When we're cranking this generator here, it's very easy to turn. There's no resistance at all because I turned the switch off. The propeller's not turning. The instant I turn this, flip this switch, I have to crank 5 times as hard. I really feel the difference, and then I get that thing to turn. Okay. why it's making so much noise. It's probably about to go. Makes for a good effect. So what you have to imagine with this dam now, with this hydropower plant, there can just be water rushing through here. Turbines are spinning freely. As soon as you turn the light on, there's that added resistance. And of course, there's so much mass flowing through, it doesn't, it doesn't stop the turning. But if the entire civilization turns on their air conditioners all at once, so that the demand for power is greater than what's actually being delivered here mechanically, then you're gonna have a brownout. Things are gonna slow down. And yeah, this is a convincer. You guys aren't here to be convinced, but if I'm turning this, somebody flicks the switch, it just becomes really easy. Flick the switch here, gotta work for it, okay? So that's one of those lessons. If you were here, we would really go over it and understand it physically, kinematically, kinetically, but as it is, you're going to have to realize that's the key important point here. It's energy conservation. Once again, you're drawing energy here, it has to be delivered over here. Okay, so that was the point to be made in this brief discussion of the laws of electricity and magnetism. And once again, see if you can get those images I mentioned in the course of the hour here to illustrate your notes a little bit more. So I'll end with where we're headed. Now that we know about electricity, well, I think I may keep that cartoon. We have just a couple more topics. So continuing, one topic is the grid. So you could say the grid, you have to understand transformers. This, I'm just gonna say, for homework, get some images. Okay. So the grid goes all the way from the power generation to our house. There's some interesting information on high voltages and low voltages and transformers. So transformers, high and low voltage. We'll see how much of this we do, okay? Having that, now we can finally start talking about solar energy. Okay, so next lecture will be about solar energy and how it ties into all of these things. It's been mentioned a few times already. A very important point. Solar energy, solar thermal power plants, of which there are a few in the region now. And they make a really good illustration of everything we've learned all semester. And conceivably a little bit about wind. All of these things, now that we have the basic physics, they're not difficult to talk over and about. So this is next time. The last lecture next week is just a complete review. And on the complete review, I'll talk about what we want to expect to do on the final, and maybe do the big full board cartoon and see if we can bring in everything we've done all semester. So that's the plan. Good. So take good notes and see you next time.